we're going to continue our notes on acid-base chemistry. So continuing the Unit 2 Part 1 skeleton notes, we had finished these two examples in class. In the second section, I just didn't finish writing the conjugate pairs. So this base is the conjugate pair with the conjugate acid, and then the acid with the conjugate base. So those are the two conjugate pairs. Okay, so now that we know what a Bronsted-Lowry acid-base reaction is, we have a proton transfer, proton being a hydrogen nucleus. We also had talked about how these reactions are reversible. We have seen the equilibrium arrow, which indicates the forward and reverse reactions can occur. And so depending on what the acid and base are and the strength of those acids and bases, the product side might be favored or the reactant side might be favored. So the likelihood of any acid-base reaction depends on both reactants, the acid and the base, and it's described as KEQ. This is something you likely learned about in General Chemistry 1. So KEQ is a ratio that measures the overall favorability of a reaction. And it is the ratio of the concentration of products, so these brackets indicating concentration, over concentration of reactants. And we talk about concentration because most reactions happen in a liquid, solution. So usually acid-base reactions are in water, but they don't have to be in water. But we can measure the concentration of the products, concentration of the reactants in that solution. So products is always the right side, reactants is always the left side. If K is greater than 1, so if the ratio is greater than 1, that means that concentration of products is higher. So we would say the forward reaction is favored. I'm going to abbreviate forward FWD. And then reaction, RXN. If K is less than 1, that means there are more reactants than products. So we'll say the reverse reaction is favored. And if K is equal to 1, that means neither side is favored. Another phrase that's used a lot in chemistry is if the reaction lies to the right or lies to the left. If it lies to the right, that means there are more products than reactants. So I'll add this note. Right above K is greater than 1, we would say this lies to the right. Products are favored. If K is less than 1, we'd say lies to the left. I think I just have to draw it down here. Which means the reactants are favored. For an acid, anytime it is added to water, it'll react with water to form H3O plus and A minus, where HA is just our general acid. The definition of an acid, a Bronsted acid, is that it donates a proton, so it donates to water. We get H3O plus and A minus. Now, you've also learned from Gen Chem that there are some acids that are really strong acids. They fully ionize in water. They will completely dissociate into its ions. But most acids are weaker than that, where they will somewhat dissociate. They will give away a proton to some water molecules, but some of the acid will still remain together. We also have to remember when we're talking about reactions like this, that when we add, let's say you have a beaker of water, you add some acid to it, you're not just adding one molecule, you're adding many molecules, like thousands and thousands of molecules, even more. And so some of those molecules will protonate or give a proton to water. Some of them will just remain as the original acid molecule, and that's again in equilibrium. So when a weak acid is added to water, we can describe the KEQ using this general reaction scheme, where we have products over reactants. So we have the conjugate base concentration times the conjugate acid, H3O plus concentration, divided by acid concentration and H2O concentration. But here's the thing, if we have a lot of water, we leave this out of the equilibrium equation. So we learn in Gen Chem to leave out any liquids, like if the phase is a liquid phase, leave that out. We include any aqueous solutions. But when we're talking about an acid in solution, the concentration of H2O is so large that we remove it from that equation because it would change a negligible amount. So we have Ka. This is the acidity constant. This is concentration of products, both ions, divided by concentration of the acid. So we just have removed the H2O. So I'm going to write a little note here. Ka is the acidity constant. It is used for dilute solutions in water. The H2O concentration is large and nearly constant. So we will not include it in our Ka or in our calculations. So water concentration just always left off. Ka values for a really strong acid that would have high concentration of product, these values range from 10 to the 14th power. So that would be for a very strong acid, lots of products and hardly any reactants, to 10 to the negative 50. So that would be a very, very weak acid that has low concentration of products. Now, because these values are so large, we in chemistry more often use pKa, which is the negative log, which is base 10, of the Ka for an acid. So we take that really large number or really small number, anywhere in between, and it becomes a more readable number. Because this is negative log, I'm going to add another note here. This is negative log of the Ka. If the Ka is really large, so let's just say higher Ka, the pKa will be low. So strong acids have a high Ka and a low pKa. Let's look at two examples. So we have sulfuric acid. This is let me tell you the Ka. The Ka here is 10 to the 9th power. So this is a very strong acid. The pKa, which is negative log of the Ka, so 10 to the 9th, is -9. So that is the pKa of sulfuric acid. It is very low. It is negative. That indicates this is a strong acid. Another example, we have acetic acid here. The Ka for acetic acid is 1.75 times 10 to the -5th. So lower Ka value than sulfuric acid. The pKa then should be higher. Its pKa is 4.76. Just take the negative log of the Ka. So both of these are acids, but they have pretty different pKa values. One is much stronger than the other. We have a pKa table that's uploaded to our Unit 2 folder on Blackboard. This will be provided on assessments. It gives some pKa values. I'm going to just go ahead and open that for us. It gives some pKa values of molecules. Now, you may see exact molecules that are on here. You may see similar molecules. We'll learn how to predict pKa values based on structure of the molecule. But what I want to show you looking at this now is just the way this table is set up. So there really are two columns, but they're continued. We have acids, two columns of acids, and then two columns of their conjugate base. So strongest acids are listed first. Here is sulfuric acid. This is the one we had just looked at with the pKa of -9. And the conjugate base would just be one of those hydrogens had been removed by a base. Notice that where we have the strongest acid with the low pKa value, so here's -9, the label up here is weakest base. Strong acids produce weak bases. Strong bases produce weak acids. That is one reason why sulfuric acid is a strong acid. Its base is very stable, so it's more willing to give away the hydrogen. Okay, so if you look down this acid column, pKa values slowly increase. We have a bunch of different molecules here. Here is, let's see if we can find acetic acid. This is acetic acid that we had just looked at. And then the conjugate base right here. And again, weaker and weaker acids as you go down that column. Then if you go back up to the right side where it says acid again, we're continuing with increasing pKa values. So it goes all the way to 49. That would be a very weak acid, but the base, now the conjugate base is very strong. So as you look at the table, these are related. We have acid and conjugate base, and that goes for all of these, acid and conjugate base. Strong acids are top left. Strong bases are bottom right. Okay, so that's our reference table. All of these pKa values are known because scientists have taken these acid molecules, added them to water, measured the concentration of the products, and compared that to reactants. That gives the Ka value, and then calculated pKa. So these are all pKa values for each acid in water. Okay, some more notes here. So reactions tend toward weaker acids and bases. We've got it right at the bottom here. Reactions tend toward weaker acids and bases. Stronger acids produce a weaker conjugate base. Weaker acids produce a stronger conjugate base. We will be able to predict whether a reaction lies to the right or left given pKa values of the acids. So that is something that will come up after we talk about Lewis acid-base chemistry. So I want to show you the next page on Lewis acid-base chemistry, and then we'll move on to predicting whether a reaction lies to the right or left in the part 2 notes. Okay, so a little bit about Lewis acid-base reactions. There really isn't much here. Bases provide electrons. That's the same thing that we have talked about for bases. In the Lewis acid-base reactions, an acid contains an electron-deficient open shell atom. So that atom accepts electrons from the base to form a complex. This is the same example that we talked about in person on Tuesday. The fluorine, I should say we talked about this when we were looking at curved arrows, but we went back to it when we talked about Lewis acids. But here it is again. So in this reaction, we see in the first molecule that boron is open shell here. It only has 3 bonds, so it can accept more. The other molecule here, fluorine, has electrons that it can share. And so in this reaction, we can see this new bond is formed. That's formed by fluorine creating a bond to the bromine. The Lewis acid is the open shell atom. The Lewis base is the electron donor, the thing that gives away electrons. And so acid-base reactions form an association product or a complex, which is the combination of the acid and base. All right, there are a number of learning checks here. I think this is what we will save for Tuesday so that we have a refresher when we are in person. Then I will move to the part 2 notes to continue learning about acid-base chemistry.